Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to have Moshe Razali here, who's going to tell us about amplitudes for Fivebranes. Thank you very much.
Thank you for the invitation. Do I have a pointer? I guess that doesn't matter. Okay, so this is based on a paper with Bartek Czech and Yutin Huang. And as you'll see, the particular slicing of that paper with a particular direction in mind, and you probably can hear a different talk about that that will emphasize other aspects. So just a brief introduction what it's going to be about. So one of the things that happened in the period of string duality is that unlike the prejudice beforehand, it turns out that there are some interacting non-trivial higher dimensional field theories. For example, the one that I'm going to discuss here, the 2-0 theory in 6 dimension. So somehow 4 dimension is no longer the critical dimension for field theory. So some of those field theories have only indirect arguments for their existence, and in particular they typically don't have a coupling constant. They sometimes don't have a known Lagrangian description. Even when there is a candidate Lagrangian, it's not clear precisely what you will do with the Lagrangian, whether you can approach the quantum theory using the Lagrangian. And in this particular talk, I'm going to discuss the 2-0 theory. The paper has a little bit more. And in particular, using a little bit the recent progress in helicity amplitude to try to shed some light on that theory. So the basic idea of using the ideas of helicity amplitude is that as long as you know what the asymptotic states of the theory, or at least you have some sort of conjecture what those asymptotic states are, you can ask what the S matrix of the theory is and circumvent some of the problem that you have when you discuss a particular formulation of the theory, for example, using a specific Lagrangian. So we're not going to talk about the full S matrix of the theory, obviously, but we're going to concentrate here on the building block for a particular part of the S matrix, which is the purely meromorphic part of the S matrix. Those are so-called the tree-level amplitudes. Now, usually you think about tree-level amplitude as the first leading part of the S matrix in some systematic approximation around the free field theory. This is not going to be the case here. As I said, this is a theory that does not have a perturbative limit, but nevertheless you can still ask under certain assumption of what the asymptotic states are, what is that part of the S matrix. Now the reason why we want to concentrate on that part is that we know how to construct it from basic building blocks. This is the so-called BCFW recursion relations. So as I'm going to review a little bit later, there is a way of constructing all those amplitudes, in other words, this particular part of the S matrix, using basic building blocks, the 3-point analytically continuous 3-point amplitudes. I'm going to describe how once you know that, once you know those, you know that part of the S matrix, and these building blocks, the 3-point amplitudes, are going to be the subject of the talk. Just get that. Yeah.
Using factor up this meromorphic part of the S matrix for everything else in an unambiguous way?
I think so. I'm not sure what you mean by factor off, but
Well, suppose I gave you the complete S matrix.
Well, is there a holomorphic part? I guess if there's something holomorphic, you can always put that in the meromorphic or in the rest part.
no. What I mean by meromorphic is a part that has simple poles and not more complicated analytic structure, for example, cuts and.
Yeah, but if there's something holomorphic, then you end up with something a bit ambiguous.
I think the ambiguity is going to be what the cut part is and not what is the pole part. Also, the other part that I'm going to say, I'm concentrating on this here, but really what I'm going to talk about is the 3-point amplitude, which would presumably be the basic building block of all the S matrix, including things that will be things that have cuts. So I'm not going to actually talk very much until the conclusions about building higher point amplitudes or any part of the S matrix from these 3-point amplitudes.
And actually another question, so how do you deal with the fact that there is no S matrix in the CFT?
Well, that's the standard thing that happens also in N equal 4, where you have certain infrared divergences associated with the fact that it's a CFT, but the structure is fairly well known. So you can think about that as, you know, for example, in N equal 4, working in 4 minus epsilon dimension. So there's going to be 1 over epsilon divergences, but their structure is known. Okay, so this is, as I said, we're going to talk mostly about the basic building blocks for the theory, and then going to speculate what this means for the structure of this theory. So what I'm going to talk about is as follows. So I'm going to talk with a quick review of 2 subjects that are relevant here. One of them is review of the BCFW recursion relation, and in particular how you can construct this part of the S matrix from the basic building blocks, the 3-point amplitudes. And then I'm going to talk about the 6-dimensional theories that I'm interested in, and in particular a little bit more about their kinematics. Okay, and then after this review of these 2 subjects, I'm going to describe a first attempt to construct those basic building blocks. The idea is that because of the kinematics, the supersymmetry, and all the other symmetries, the 3-point amplitudes are very much restricted. And as we'll see, the first attempt has failed, meaning that you don't find any possible 3-point amplitudes, which is a little bit puzzling. So after this first disappointment, what I'm going to talk about is what guesses you can make in order to relax a little bit the assumptions and get non-trivial amplitudes. One of the things that we'll do is go down to 5 dimensions from 6 dimensions. And we'll see that in 5 dimensions we do have a few interesting results. We're going to find 2 possible amplitudes. And I'm going to conclude with 2 intriguing directions to do with the higher point functions and some gauge algebra that we find, and conclude. Okay, so this is the basic building points. So I have to say, actually, as an introduction also, that I'm not going to talk very much about the specific details. I'm going to review a lot of those more technical details, and hope that you come with questions if you have specific questions. As you can see in the first slide, this is very schematic already. So the basic idea of the BCFW recursion relation is that you can express endpoint on-shell 3 amplitude as a sum over product of lower point amplitudes. So this is a little bit like a factorization channel of Feynman diagrams, except there are some twists there. And some of the twist is that the building blocks in this recursion relation are by themselves on-shell lower point amplitudes. Okay. So roughly speaking, what you are going to do to calculate an endpoint on-shell amplitude is you mark 2 privileged external legs I and j for special treatment. I'm not going to discuss precisely what it is. And then the recursion relation is going to be, you write them as a sum over all partitions of the external line, cyclic partitions, in which I and j are separated by an internal line. And the amplitude, the sum is over product of the amplitudes as written. It's a product of 2 lower point amplitude times a propagator, a regular scalar propagators, in some shifted momenta. And the main point of that recursion relation is that those lower point amplitude are by themselves, they're complexified, but they are by themselves lower point functions that are on shell. So you never need to go off shell, you never need to commit to a specific quantization scheme. This is some relationship between observables. Okay. The other important point is that because of this special treatment that makes those ingredients on shell, those are complexified. So in particular, you can see that when you use this procedure iteratively, you can reduce any amplitude to a product, a sum over products over 3-point functions. And it's very important that those are complexified because 3-point functions in a Lorentzian spacetime of massless fields are going to be 0. Nevertheless, when we discuss complexified amplitudes, those building blocks are non-zero and they encode a lot of the information of the theory. So for example, if we discuss gluon scattering in 4 dimensions, then the 3-point function is going to be determined just by kinematics and basic symmetries of the problem. So the momenta and polarization of gauge fields of gluons can be built from bosonic spinors, which are lambda and lambda twiddle. So we have to think about those things as carrying 2 kind of indices. Even though in 4 dimensions they're particularly simple, they carry Lorentz indices, they're spinors. And because there's lambda and lambda twiddle, that means that they're spinor of either SC2 or the other SC2. And they carry little group indices. The little group is particularly simple in 4 dimensions, so they carry charges which are opposite to each other with respect to the little group. Okay. So the amplitude is going to be a Lorentz invariant combination of those spinors, and you can identify it as amplitude of certain types of external states by the little group indices, or the charges, or the little group transformation of those external legs. So for example, for 3-point amplitudes, if you want 2 of the external legs to carry negative helicity, and 1 of them to carry positive helicity, this determines the 3-point amplitude uniquely. Okay, where I use the notation of the standard notation of angular bracket, which denotes the Lorentz invariant contraction of 2 spinors. Okay, so this is unique in the sense that this is the only way that you can construct something that transforms in the right way with respect to both Lorentz transformation and little group transformation. So this is the basic idea of using this sort of procedure to discuss the 3-point functions of the 2-0 theory, where the kinematics is going to be a little bit more complicated, but because the structure is so simple, you can try to restrict what are the type of 3-point functions that you'll find. And as I said, once you find these basic building blocks, you can hope at least to find higher point functions by fusing together those basic ingredients, in other words, using the BCFW recursion relations. So this is a way to approach the quantum theory directly by concentrating on the observables and not about a particular way of quantizing a Lagrangian. Okay. And the last paragraph here is a caveat. The BCFW recursion relation are not universal. They work under a certain assumption, their technical assumption to do with convergence of certain expression. And for 4-dimensional super Young Mills, you can prove that because you have a definition of the theory, you have a Lagrangian, you can define the theory using Feynman diagrams. It's not necessarily the best way to calculate in that theory, but you can use that definition to prove those technical assumptions. Now, the 2-0 theory doesn't have a similar definition or similar way of calculating, so we will have to assume that those relations hold, that these technical assumptions hold, and yeah.
So if you wouldn't know the Lagrangian and supersymmetric Yang-Mills, would you in this way discover the need for the 4-point vertex?
Well, there's no need, in this formulation there's no need for a 4-point vertex because we're discussing on-shell amplitude only. So you can construct 4-point function using only those 3 vertices, and you get the result that you would get from Feynman diagram using the 3 and 4 vertices. So it's a little bit different from Feynman diagrams. Okay, so this is the standard caveat. Since we don't know about this theory, we assume this is correct. As we'll see, there are certain consistency conditions that follow from the BCFW recursion relation, and we checked at least some of them, and they do hold in this case. Okay, so the consistency condition, as I said, so as I started discussing, in order to use the BCFW recursion relation, you mark 2 external states for special treatment. Of course, you can mark different states. You're going to get then different decomposition of the same amplitude. So you're going to get many, many different ways of constructing the same amplitude using different BCFW decomposition. And of course, they all have to be the same. So this gives you a particular consistency condition. For every higher point amplitude, you're going to get a set of consistency conditions resulting from the fact that you can construct it differently using lower point amplitudes. So in particular, this is a set of consistency conditions on the basic 3-point vertices. So one of the interesting things that happened in the n equal 4 in the super Young-Mills, it doesn't have to be n equal 4, is that part of this consistency condition has to do with the color factor that you assign to external legs. So if you assume that the external legs have some abstract vector index, so there's some multiplicity associated with that external leg factor, then you could see that the consistency condition of the 4-point function, the fact that you construct it differently from 3-point function, gives you a restriction on that external leg factors. So if you associate some abstract tensor FABC with any one of those 3-point functions, you find that those FABCs have to obey the restriction you get from a gauge algebra, from a Lie algebra. So somehow you don't have to assume that those amplitudes are amplitudes of a gauge theory. You can discover that from the BCFW recursion relation. Of course, this is a very interesting thing to repeat for theories like the 2-0 theory. Questions? Yeah.
You do this for 3 dimensions? Do you find like 3 algebra structures and so on?
I don't know the answer to that. I think people have done that.
I think there was a paper like last week.
Okay.
Tristan McLaughlin and some collaborators, which basically that's the case. And actually, Akani Ahmed told me once that was the case.
So they found the 3 algebra from that. Okay, that's interesting. Okay. Okay, so let me summarize that point, because this is going to be the rest of the talk here. So basically, we're trying to construct these 3-point vertices with the hope that that's going to give us some alternative definition of the theory. And the constraint those 3-point, I call it vertices, but it's really 3-point amplitudes, have to satisfy the following. They have to transform correctly under the little group transformation. In fact, we're going to construct all possible vertices, and then after the fact, we're going to interpret, using the little group, interpret them as amplitude of specific states. They have to transform the right way under Lorentz and supersymmetry. Because there is some knowledge about the 2-0 theory when it's compactified to either 5 or 4 dimension, then we have additional constraints on those amplitudes. Namely, when you reduce them to 4 dimension, they become the n equal 4 amplitudes. When you reduce them to 5 dimension, they become the super Young-Mills amplitude in 5 dimension. So those are restrictions. As we'll see, there's going to be a non-trivial restriction from S-duality. And finally, they have to have the correct limit as the momenta become real. So those are not by themselves observable because the momenta are complexified, but as the momenta become real, some of the expression that you can write become infinite, and you have to disregard those expressions. So those are a lot of restrictions on the basic three-point amplitudes, and the idea was to try to use those restrictions to determine those amplitude, or at least to see what are the range of possibilities. Questions? Okay. So that was part one of the introduction, which is introducing the part of the helicity amplitude machinery that we'll need for this talk. The other part is going to be very, very fast to just discuss the 2-0 theory and the parts. There's a lot known about it. There's a lot not known about it also. And just the part that's going to be relevant for this talk. So the 2-0 theory is the world volume theory of the M5 brane. We're going to mostly discuss separated M5 branes, namely, meaning on the Coulomb branch of that theory. And when they're separated, you can do collective coordinate analysis of a single M5 brane, and you identify the modes that live on that 5 brane, and they live in a tensor multiplet of a 2-0 supersymmetry. So this tensor multiplet includes the self-dual tensor field, and it has an abelian gauge transformation. The gauge parameter is a vector rather than a scalar. So in some sense, it's generalization of an abelian gauge field in 4 dimensions. And one of the interesting things about this theory is that it's related to various theories in either 4 or 5 dimensions. So for example, when you compactify the 2-0 theory to 4 dimension on a torus, you dimensionally reduce that theory, you get the n=4 super Young mills. So this is one of the reasons it's interesting. There's also an interesting connection to 5-dimensional gauge theory. That's going to be one of the tools that we'll use. So once you put those those M5 branes together, then the theory becomes very mysterious. The equivalent of the W bosons, that for D3 branes will be just strings connecting separated 3 branes that then become massless. The equivalent of that is going to be states of some strings, membranes ending on the 5 branes, that become in some sense tensionless at the origin of the Coulomb branch. And it's believed that the theory becomes a strongly coupled CFT with no tunable coupling constant at the origin of the Coulomb branch. Okay, so this is the motivation to look at that theory. Okay, so now that we have the basic subject cleared, let's see a little bit about the technicalities. So we want to do something like I did very quickly at the first transparency, that constructed the 3-point amplitude of super Young mills just from requirements of symmetry. So first of all, I'm going to talk about the kinematics of those 6-dimensional theories. They're a little bit more complicated. So the thing that I didn't talk about before, and is still true in n=4, I talked about just gluons, but it's easy to generalize to n=4, is that you organize the degrees of freedom in on-shell superspace, and it's a chiral superspace. So in this representation, the little group is going to be manifest. Now, the little group in 6 dimension is larger, so those charges plus or minus 1 are going to generalize to SU2 representations. So those will be the equivalent of helicities. And the 2 supersymmetry generators, or actually any number of them, if you talk about different theories, carry little group in this as well. And the supersymmetry that we're interested in this paper is always chiral, so we discuss either 1-0 or 2-0 supersymmetry in this talk. So that means that the generators, the superchargers, transform only in one of the SU2 factors of the little group. Okay, so well, I give an example. We can skip that quickly for the interest of time. And let me just say that the massless multiplet of 1, 0 supersymmetry are vector, scalars, and tensors. And the massless multiplet of 2, 0 is the tensor multiplet, which decomposes under 1, 0 supersymmetry as a vector, as a tensor plus scalar, no vector. So those are the basic organization of the fields. Now the amplitudes themselves, which are going to be interpreted as 3-point amplitude of those fields, have to be constructed from the momenta of the external states. And what we're going to do is, what we did was classify all possible functions of the external momenta that obey those restrictions that I discussed before, and interpret them as 3-point amplitudes of some degrees of freedom that exist in the theory. So we classify all possible functions, and after that classification, we see what possible 3-point functions exist. Just one technical point, because the little group index identified the supersymmetry multiplet uniquely, it's actually possible to work at the level of super amplitude here, or directly work at the level of multiplets. So this is the basic idea. So the basic building blocks are going to be those external momenta. As before, it's better to use some spinor representation of those momenta. Now there's something interesting that happened in 6th dimension, which is different from 4th dimension. In 4th dimension, in order to write a spinor representation of a momentum, you have two types of spinors. You have what I called before lambda and lambda twiddle. But in 6th dimension, the representation is a little bit different. You have two alternative representation. Either you have two spinors lambda A, where A is an index of the little group, which is chiral. So the little group, again, is SU2 times SU2, and A is going to be an index of one of the SU2 factor. And when you have those two spinors, then you construct the momenta from those two spinors by themselves. Or alternatively, you can take two spinors that transform with respect to the other factor of the SU2. So in other words, you can construct the momentum in 6th dimension using chiral spinors, which is not the case in 4 dimensions. Okay, so this is a hint that there could be an interesting chiral structure in the 6th dimension. Nevertheless, the only Lorentz invariant product involves contracting lambda with a lambda twiddle. Okay. So basically, in order to construct amplitudes, and again, we're later on going to interpret what amplitude they're of. In order to construct amplitude, we are going to construct all possible functions of those variables, lambda 1, lambda 2, lambda 3, and the same with the twiddles, and interpret them after the fact. Now there is a technical point here which I'm not going to discuss in detail. Instead of talking about those spinors, which are spinors of Lorentz symmetry and constructing all the Lorentz invariants, we can trade them specifically for 3-point amplitudes of massless states. We can trade them for a convenient set of variables that are already Lorentz invariant. This is what I called U and U twiddle. So there are 3 of those, the 3 U's and 3 U twiddles. And you can construct also other building blocks, which I call W, W and W twiddle. And all of those things are already Lorentz invariant, but the W's are ambiguous. There is a certain ambiguity, which we discussed in the paper, in constructing the W. And when we construct amplitude using W's, we have to make sure that they're unambiguous. But nevertheless, it's easier to construct amplitude using these basic building blocks because they're already Lorentz invariant. Okay. So again, the point is to start with these variables and construct all possible functions with the right properties, and then interpret what do they correspond to. Okay, so at that level we can discuss what are the supersymmetry constraints. For 3-point amplitude to have n0 supersymmetry, I'm going to talk mostly about 2-0, but we constructed cases where n goes from 1 to 4. There is a certain form of the amplitude as written that guarantees that those supersymmetry constraints are satisfied, and this form determines the amplitude up to an unknown function f. So this is f of those variable u and w. And as far as supersymmetry is concerned, this f is arbitrary. But of course, the full amplitude has to satisfy constraints. Most importantly, it has to be unambiguous. Again, those w variables that I discussed are ambiguous. So when you construct amplitude using the w's, you have to make sure that the full amplitude is unambiguous. And we classified all the possible f's. And then again, when we classified all of those amplitude and inspect the little group indices, we can interpret all the possible 3-point function of all possible multiplets of either 1-0 or 2-0 supersymmetry. Let me skip this last point here. Okay, so first you do it in 1-0 supersymmetry in 6 dimensions. And we find that already there are only 3 possibilities for amplitudes, and the following 3 possibilities are scalar vector 3-point function, or vector. Both of those are amplitudes that you recognize from Young-Mills theory in 6 dimensions. And there's an additional amplitude that's allowed in that satisfies all those constraints, which is tensor vector. So it's roughly B wedge F by wedge F amplitude. Okay. So the point here, then we had some discussion in the paper on the implication for 1-0 theories. But the point for the 2-0 theory is that there is no interaction possible. So as I said before, the 2-0 tensor multiplet decomposes under 1-0 as a tensor plus a scalar. And you can see that there is no amplitude involving only scalars and tensors. So this is a little bit puzzling. And so as far as the 2-0 theory is concerned, in 6 dimension you cannot write any 3-point vertex for the tensor multiplet. Now the next thing that we did was then discuss if the tensor multiplet can interact with higher spin massless multiplets of 2-0 supersymmetry. And the results there were disappointing as well, because we found some 3-point vertices that involve the tensor multiplet and some higher spin multiplet, but we find that any such theory will contain gravitational couplings as well. This is an argument from channel duality that I can discuss in private later, but the upshot of that is that any theory with tensor multiplet and any other multiplet necessarily includes gravity in 6 dimensions. Okay, so this is the disappointment. There seems to be no way to use this machinery. Of course, this machinery has certain assumptions, so it could be that those assumptions are incorrect for the 6-dimensional theory. But the first naive way to just go ahead and see what are the possible ways to construct those 3-point amplitudes has failed. Yeah.
Can I ask about these assumptions? When people did this sort of amplitude work, weren't they sort of assuming the existence of perturbation theory, and that some of these formulae that you put up were there really as only tree level or even a loop, but there were still perturbative formulae?
No, I don't think that's necessarily the case. I mean, I think the best success so far of the holistic amplitude formalism is to calculate things simply. But it could also be, because it only uses on-shell amplitudes, it could also be an alternative way of formulating theories. And I think there's been some cases where you could do that for certain theories. So I don't think it assumes perturbation theory.
Yes.
Well,
Another little question.
Yeah.
So lambda, lambda, tilde were chiral 6-dimensional
so
spinors.
that's right.
And there is no way you can reduce them by imposing something like a pure spinor condition.
I don't
Would this
know,
affect?
but that might be another way to go. I mean, I'm going to talk, the next transparency is going to start talking about what did we do in order to deal with that disappointment, but there might be other ways. Yeah.
So one conclusion could be that there's no three-point function. That's on-shell three-point function.
Well, that's right.
Okay, no?
I mean, there could be theories. So, for example, there could be theories that have irreducible 4-point functions only.
I mean, membrane theories won't have to have three-point.
Well, let's talk about that in private, because if we try to construct 4-point functions that don't reduce to 3-point function, then specifically for these theories you have some difficulties. But yeah, there could be ways around that. So again, it could be that the assumptions somewhere, there are some assumptions there, some of them are implicit. There could be ways in which, yeah, this is just the answer. Okay.
And sorry, and you would be okay if you threw in a vector multiplier.
Sorry?
Your observation is that you don't want any vectors.
Well, the tensor theory doesn't have any vectors, so. Well, maybe it implicitly does, but.
Well, there's this D2 category description of gerbs in which there is a vector here.
That will help a lot. So maybe we'll talk about that too. Anyway, what we did is the following. We relaxed the assumptions in a certain way. And again, that way might be a sensible way, or it might not be a sensible way, but at least it enlarges the number of possibilities. So the idea was that in order to use this formalism, you need to know that you identify the asymptotic states. This is the big assumptions there. So the question is, did we identify the asymptotic state correctly in this theory? And the asymptotic states so far were massless tensor multiplet. So on the Coulomb branch, the theory has, in addition to the self-dual multiplets that we discussed so far, it also has states of some membranes that end on the Fivebranes. Those are formally strings on the world volume of the Fivebranes, and those are massive strings when you go to the Coulomb branch. And presumably there are some string-like states in 6 dimension corresponding to scattering of those states. And perhaps the problem is that we don't know how to represent those string-like states as asymptotic states in 6 dimensions. Because again, the string-like states, they're not particle-like states, so you cannot construct plane waves from them and discuss scattering the usual way. So one way around that is to reduce to 5 dimensions, where at least wrapping modes of those strings will be then particle-like, and you could envision discussing them using this formalism. So you identify some scattering state that correspond to wrapping modes of these string-like states, and discuss them in 5 dimensions on the Coulomb branch, and see if that is going to help. It's going to enlarge the number of possibilities, as we'll see it does. Once you reduce to 5 dimension, almost immediately you find 3-point functions involving exactly such states. Okay. There's also another motivation, which is a little bit more speculative. is that it could be that the 2-0 theory can be defined as a strong coupling limit of the 5-dimensional super-Young-Mills theory. You can already see that the states needed to complete the 6-dimensional picture are already, in some sense, exist in this 5-dimensional description, and we'll see a little bit more evidence of that in the sense that the 5-dimensional description will also give you some information about the scattering of such states. So there'll be a little bit of a connection to that line of thought there. So again, we're going to do exactly the same exercise, but now in 5 dimensions. So we organize all the particle-like asymptotic states by 5-dimensional kinematics, but we're discussing both 5-dimensional massless and massive states. So the theory is really, in some sense, 6-dimensional. Now, each asymptotic state could be identified uniquely as having a reason, as coming from a particular 6-dimensional modes. You can identify it by either the kinematics or by a certain identification of the central charge. And we'll see that we'll just have more of the states that you expect from the 6-dimensional theory. In addition to have a Kaluza-Klein modes of the 6-dimensional massless field, we'll also have those states that I described in the previous transparency corresponding to wrapping the string-like states in 6 dimension down to 5 dimension. Okay. Good. So basically, once we work in 5 dimension, we're going to have still very restrictive assumptions, but the assumption, as we'll see, will allow more non-trivial amplitudes. And as before, those amplitudes have a specific form, but they also will fix the matter content involved. So you write all the possible functions of the restricted kinematics, and you identify what are the asymptotic states corresponding to all those amplitudes. And as we'll see, we'll have more possibilities here. So very briefly, what do you do in 5 dimension is very similar in idea to what you do in 6 dimension. You have a kinematics that is fairly similar to what we had before. So asymptotic states are characterized now by spinors of 5-dimensional Lorentz group, and they carry little group indices. Now we're mostly interested in massive states. Massive state little group in 5 dimension is exactly the same as massless state little group in 6 dimension, namely SU2 times SU2. And those spinors we're going to call lambda, the same name that we called before. And we're also interested in massless 5-dimensional fields, and we have to be careful about taking that limit, of course, because the little group in 5 dimension is smaller. So if you take the supersymmetry constraint, we get the same form of the amplitude as before. There is a factor needed in order to satisfy the supersymmetry constraint, and you still have an arbitrary function of those basic variables that I discussed before. But the point is that now you have more invariants to play with and construct a function f, and this leads to a large number of possibilities. So when we reduce down to 5 dimension, we actually have too many possibilities. Before we had no possibilities for the tensor multiplet, now we have a lot. And the thing that helped here is the requirement of S-duality when we reduce down to 4 dimension. So again, this is a little bit of a technical discussion, and we can talk about the details privately. But there is a scenario that was advocated by Douglas that provides us with a constraint. Namely, when we reduce down to 4 dimension, then if we actually truncate the theory and discuss only the massless spectrum, then we have n equal 4 super Young-Mills, which is S-dual. So in particular, there is certain restriction of S-duality on the 4-point function. And now, when you include all the massive Kaluza-Klein modes, So in other words, you don't dimensionally reduce the theory, you just write it in 4-dimensional language. The extension also should obey S-duality, which is just a geometrical duality of the torus if you compactify the 6-dimensional theory in the torus. And there is a scenario advocated by Douglas where these constraints satisfy, in some sense, in the simplest way possible. And again, this, if you want, is a particular restrictions on the amplitudes of those Kaluza-Klein modes. And again, for lack of time, I'm going to omit the technical details here, but the point is that this requirement of S-duality cuts down the number of possibilities, which became very large, cut it down to a very small number again. The number of amplitudes now is going to be precisely 2. So we're going to get 2 possible amplitudes in 5 dimensions now. And let me describe those 2 amplitudes. So we have 2 possibilities now. The first one is the easiest one to describe because it doesn't involve any new states beyond what we had before, which was the 6-dimensional self-dual tensor multiplet. So as we saw before, there's no pure tensor interaction. So similarly, and almost obviously, there's no massive Kaluza-Klein mode tensor interaction that in 5 dimension, because that will lift up to 6 dimensional to the amplitude that we saw is forbidden. But we can have a new amplitude which you can have 2 massive tensors. Those are Kaluza-Klein reduction of the tensor multiplet in 6 dimension, and they couple to a 5-dimensional massless vector. And that vector is massless, so you cannot really lift this amplitude to 6 dimension. And this comes from this particular choice of the function f. So this is kind of an interesting amplitude. As I said, it's not possible in the 6-dimensional limit. It's only possible in 5 dimension. Now, if you take the opposite limit in which all states are massless, so the tensor multiplets, when you Kaluza-Klein reduce them, and you only take the massless mode, the 0 mode, they're equivalent to vectors. So what you get from this interaction is the vector-vector-vector interaction of 5-dimensional super-Young-Mills, and it's indeed identical to what that interaction is. So in some sense, this is an extension of the 5-dimensional super-Young-Mills interaction, which is chiral in the 6-dimensional sense. Okay. Questions? So this is one of the new interactions. The other new interaction involves a new type of multiplet, which I just call the massive tensor here, but you can find any other name. So this is so again, we classified all possible functions, and we discovered that an interaction is possible with this specific multiplet. So in some sense, we rediscovered that multiplet. This multiplet was also discovered before in the context of those membranes, the open membranes that connect between Fivebranes. So when you quantize those, you find this particular multiplet as well. So this is a short multiplet. It's carrying central charges that identify it as a winding mode. So you have this particular bosonic on-shell degrees of freedom that involves these self-dual tensors, vectors, and scalars. So significantly, it has vectors in it, unlike the self-dual multiplet. So in some sense, the vectors corresponds to the fact that this is a massive mode in which the tensor has become massive now. And that might be one way in which this fundamental puzzle that I mentioned here is resolved. The tensor multiplet itself has this particular gauge symmetry. It's a shift by a vector, unlike a shift by a derivative of a scalar for the gauge field in 4 dimension. So in order to break that symmetry, which is what you think you're doing when you separate the Fivebrane and go to the Coulomb branch, you need to have something charged under that symmetry, and the tensor multiplet itself does not have anything charged under that symmetry. It has scalars, it has fermions, it doesn't have any vectors in it. And in some sense, this particular multiplet has the right matter content in order to implement the Higgs mechanism. But nevertheless, this is an interpretation of the result. The result we find is that when you write, again, all the possible functions, one of the two possible interaction involves this particular multiplet. And the interaction is of the form WWT, where W is this particular multiplet, and T is the self-dual tensor multiplet. So this is also an interaction that you get between a gauge field and a charged matter field. If you think about the W as W bosons of a gauge theory in the Coulomb branch, you would have there a W plus, W minus A, where A is the photon. So this is the same type of interactions. Okay.
I'm a bit
Yeah.
confused. That abelian transformation of B,
Yeah.
I mean, sort of the self-dual string is the thing which is charged in the back.
That's right. That's right.
So what's your statement that
Well, the statement is that if you want to break the in N equal 4, if you want to go to the Coulomb branch and separate the branes, the way you do it is you give Vev to some fields in the vector multiplets.
but that's I mean, but this is the overall you want. I mean, so that would still persist in N equals 4. I mean, because that would be just taking UN to U1 across SUN.
Well, that could be the relative U1 of two.
That's in the relative U1, but this is always, I mean, this B, isn't that always the center of mass?
It could be either, but I think the interesting statement would be about the relative U1. Yeah. The other one is free, and that's right.
That's why
That's right. This would be the relative U1. You need something that's charged under the relative U1, and the point is that that in the D3 brane description of N equal 4, you already have it in the vector multiplet. You have scalar fields that are adjoints with respect to the gauge symmetry, and when you give them Vev, you get the right symmetry breaking, the expected symmetry breaking pattern, which is not the case here. Okay. So I'm almost concluding here. I have two kind of puzzling observations that we found along the way that could be interesting hints. One of them that we find is a particular fermionic gauge symmetry. So I discussed before the bosonic on-shell degrees of freedom of this multiplet, but this multiplet also has a spin 3½ fermion, and it's not the Gravitinov 2-0 supersymmetry because it has an anti-chiral index. It carries an anti-self-dual spinor index, and it's also a self-dual Thun tensor. And it can be thought of as a generator of local supersymmetry. So in some sense, we have a 2-1 supersymmetry, which is accidentally enhanced supersymmetry for this particular multiplet. In fact, what we did in the paper is we wrote a local supersymmetry transformation on that multiplet, and we verified that this is a symmetry of the free equation of motion. And one of the most intriguing things is that when you do successively two such supersymmetry transformation, they close to a tensor gauge transformation rather than to a translation. So this is why you can have a spin 3½ spin 3½ state in a theory that doesn't have gravity. So again, the anticommutator of two supersymmetry transformation is going to be that abelian tensor gauge transformation.
Doesn't close onto momentum.
No, it closes.
It's not Poincaré.
No. Yeah, so this is kind of an interesting loophole because you can have two supersymmetries that close because you have this vector gauge symmetry here, which is an unusual object. Then you can have that kind of supersymmetry here, which is interesting. So, yeah. So this seems again. So this seems to indicate something about the how you enhance the tensor gauge symmetry of the theory. So the abelian tensor gauge symmetry I wrote before, there is in some sense a non-abelian structure that enhances that when the Fivebranes are coincident, and somehow this gives a hint that that gauge symmetry should have a fermionic part. Because again, there is at least in the Coulomb branch, there is a fermionic symmetry such that two fermionic symmetries antacommute to a gauge symmetry. So again, it would...
Means that physically you don't have to have a partner. I mean,
Sorry?
it's only when you have something like Poincare asymmetry. I mean, there is a real one on the right-hand side of your commutator algebra that you're forced to introduce the superpartner. If it's only a gauge transformation,
That's
you
right.
maybe get away with it.
It's more
Yeah,
like,
that's right.
It's more like a BRS.
Yeah,
Yes, yes.
that's right. Yeah, yeah. So again, in any way yeah. So this might be a good hint on what is the underlying algebraic structure of this theory. Okay. Okay. So the other intriguing direction is the higher prone function. So I'm going to talk about that very briefly. So I said before, there is certain technical assumptions in using the BCFW, and of course we don't have access to the theory in any other way, so we don't know whether those technical assumptions are justified or not. But there are some consistency conditions that follow from those technical assumptions. So the first thing that we can do is to check whether those consistency conditions apply. So one check that we have performed is constructing the 4-point functions, a particular 4-point function, the AATT amplitude, in two different ways, using different BCFW constructions, and find whether or not you get the same expression, and you do. Okay. So again, the study of higher prone function and the consistent condition is very interesting future direction. In particular, before, in the super young Mills case, I said that there is a way of discovering that you have a Lie algebra structure there, because if you assign some tensor to the 3-point function, you find that that tensor is associated with the Lie algebra because it has to satisfy all those constraints. Those come just from consistency conditions. So you can try to play the same game here, and we haven't, and see what are the consistency conditions on the vector structure associated with those external legs. So let me conclude. So there's no complete picture here of the dynamic of the 2-0 theory, but I think we found some clues on what could be the dynamics there. One clue is that by basically doing just kinematics and a few symmetries, by requiring just the basic kinematics and a few symmetries, we discovered that this multiplet, which I call W, is pretty much the only thing that can induce an interaction for those tensor multiplets. And somehow it seems important, at least on the Coulomb branch, to understand the dynamics of that theory. The other intriguing thing, as I just said, is the fermionic extension of the abelian tensor gauge symmetry. That seems like it could be a new direction to go to. It is interesting that somehow it's necessary to go down to 5 dimension in order to discover any non-trivial structure here. So somehow, at least if you want to use this machinery associated with scattering theory of with scattering in this theory, then you have to go down to 5 dimension. And finally, something that I didn't discuss is that there was an interesting extension of all this story for 4-0 supersymmetry. Okay. So.
Any questions?
So on the slide before you had AATT.
AATT.
A is the gauge field and T is the tensor.
That's right. In 5 dimensions. So A is the massless gauge field and tensor is the massive tensor.
Do you have anything to say about the 4-0?
On
On the last point, 4-0.
well, I mean, there's a few amplitude that we wrote in the paper, but as the story for the 2-0, I'm not really sure what that tells you about the theory itself.
Is that theory meant to not have gravity or have gravity? Chris Howell talked about.
So this is a theory when you reduce the 5-dimension become a 5-dimensional supergravity. But it's chiral also. So in some sense it's analogous.
Does it have a graviton in 6?
Uh,
I don't know. Why doesn't it? Wow. 2.0 doesn't have a gauge field.
Unconventional.
I mean, is there a spin 2 state in the 2.0? The 4.0?
I think there's not something.
I think the answer is no,
Yeah.
as far as I can remember.
Yeah, let's call a graviton a spin 2 object.
Yeah, well, okay.
I think the answer is no as far as I'm remembering, but yeah.
Well, you're here for a week or two.
A week from the week and
I'm
the
sure
day.
there's lots of questions people have to pursue that a bit further. Let's speak again.